All right, let's take a look at this check on entropy. So entropy is the measure of molecular randomness or disorder. And so I kind of think of this as, how our rooms, our bedrooms are always constantly kind of going towards disorder. And we actually have to put energy and effort in to clean it. And so that just naturally tends to go towards disorder. So we're going to take a look at a few different things under entropy today. Positional probability is the first one. And so with positional probability, this would be the highest likelihood or probability. Okay. Of molecules to be in a given location. So how many different possibilities are there? And the more possibility, or the higher the probability, the more likely that would be. And so let's take a look at a few examples of these with gases and solution formation and phase changes. So those are going to be our three. So with gases, we know that gases expand. So they're going to fit the container that they're in. So they're going to have increased probability for those gas molecules when they spread out. MLQS is my shorthand for molecules to spread out. I use a little goofy there. If we're looking at phase changes, or the state of matter that something is in, we're going to see that the lowest entropy, let's just use delta S because that's going to be easier, delta S, is in the solid state. And then the next one would be a little bit increased of entropy would be in liquid. And then, of course, the greatest is going to be with gases. Okay, so that's going to be the highest delta S. And then finally, if we're looking at solution formation, okay, you're going to see that entropy is going to increase. So we're going to have an increase in entropy, delta S, as molecules spread out. In a solution. Okay. So there's a little bit more about positional probability in the textbook on page 792. So you might want to take a look at that and get a little, maybe a little bit better explanation or a more thorough explanation. But those are some examples of how that works. So with the second law of thermodynamics, we know that spontaneous processes always increase the entropy of the universe. This is a little bit arbitrary for us because we really take a look more at Gibbs free energy when we're really evaluating spontaneous processes. But just for now, let's take a look at this in context of the delta S of the universe. And so delta S of the universe is, of course, equal to the delta S of the system plus the delta S of the surroundings. And in chemistry, we actually can measure either the system or the surroundings. A lot of times we measure the surroundings. And so what we're looking for is a positive delta S for the universe. Again, I think this is a little arbitrary because we usually evaluate this with Gibbs free energy, but just to make sure we kind of understand it in the context of the second law of thermodynamics. And so in this case, we're going to take a look at this part here, which is delta S of the universe is determining spontaneity and then the question becomes which factor, okay, which one of these two is going to be the deriving force. Okay, so which the system or the surroundings is going to be driving the outcome of this. And really for this, it really depends upon temperature. It's temperature dependent. And remember, in this particular case, we are working with units of Kelvin. Okay, so then we're going to look at those important factors for the surroundings and kind of evaluate this whole temperature thing. So the two important factors for the entropy of the surroundings, the first one is going to be the sign for the entropy of surroundings. And that is going to depend on heat flow at a constant temperature. Okay, so we see a positive delta S of surroundings is going to be an exothermic situation, and a negative delta S of surroundings is going to be an endothermic situation. The second thing that we need to take into consideration here is the magnitude of this value. So magnitude of the entropy of the surroundings depends on temperature. Okay. And so here we see an equation. It's equal to the negative enthalpy, delta H, divided by T. I would say we don't use this equation a lot. It's not something you see on your equation sheet, but it is some way that we can evaluate some of these entropy considerations. Okay, and so when we look at entropy change and spontaneity, and this is, like I said, this is just in context of looking at entropy. We're not considering delta H or delta G in this particular one, which I think is far better for evaluating what's going on in our overall process, but we're going to go ahead and kind of look at this just in this context. So if we have a positive system, we know that it's going to be spontaneous. And so in that case, if everything is positive, we have no other choice other than to get a positive delta S of the universe. Oh, excuse me, the universe is going to be the one that we want to evaluate. So this is the one we want to evaluate. Okay. And so if both of these, the system and the surroundings, are positive, we're going to have to get a positive. If they are both negative, okay, then the universe is negative and it is not spontaneous when it comes to the context of these. Finally, the question becomes, what if one is positive and the other one is negative? So let's look at these two situations. And we don't necessarily know. We have to take into consideration what else may be going on. So it would be spontaneous for this first one if we have the system is positive and the surroundings are negative. So this would be yes if there is an increased or a higher amount for the delta S of the system. Okay. And the bottom one is yes if it has a higher amount or greater amount of the delta S of surroundings. Okay, and if you ever forget those, if you're looking at an equation like this, for example, up above here, you can actually plug in some arbitrary numbers just to see what happens. I wouldn't worry about that too much with this situation, but I think there's some other situations where that could come in handy. Okay, so let's take a look at entropy changes in a chemical reaction. So if we are looking at a change in a chemical system, and we are looking at positional probability, which really helps us, then we can take a look at this homogeneous gas reaction. So if we have everything is in the gaseous state, okay, we're going to compare moles of gas. We're going to have a positive delta S entropy if the moles of products are greater than the moles of reactants. Okay, and vice versa. So if we have a negative entropy, if the moles of products are less than the moles of reactants. Okay. So let's take a look at an example here. So what is the sign of our entropy for each of the following reactions? And actually we just have one here. We're going to take a look at a couple different situations. So in the first one we have 2 moles of gas and of course this is a homogeneous gas situation. Everything is gases. That's why we have the homogeneous. Okay, on the left hand side, and then on the right hand side we have a total of 3 moles of gas. So we have 2 here and we have another 1 mole, so that gives us 3 moles. And so in this case, we see the situation where the moles of products are greater than the moles of reactants. Okay, we see this situation, and so that's going to tell us that we have a positive delta S. Okay, this is the situation that we see down here, so positive delta S. Okay, let's take a look at a heterogeneous reaction situation and what we need to consider there. Okay. So under these circumstances, it's going to be positive entropy if the change increases particular motion or position. Okay, and vice versa. Okay, if that change or that chemical reaction decreases, or process, it could be a physical process as well. Of course, we're working with reactions right now. Okay, so let's take a look at some examples and see if we can figure these out. So in the first one, we are going to, from a gas, okay, so in this case, we're going from a gas. So these are heterogeneous situations, right? We do not have everything in the same state of matter. And so on the left-hand side, we're going from a gas. Everything's in gases. And on the right-hand side, we have liquid. That actually is decreasing. Okay, so that's decreasing particle motion. And that would mean we would have a negative delta S here. Okay. In the next one, we're going from a gas to a solid. Definitely the same thing. We are going to be decreasing that particle motion. Okay, so it's the same thing. Those molecules move slower in the solid state, so decreasing particle motion. And so we definitely have a negative delta S. Okay, that's not the natural way that things would go. Things go from a solid to a liquid to a gas. That is the natural way that natural tendency of things that we see. Okay, and then in this last one, we see that we have a solid that is changing into a solution, okay? With the aqueous. That is going to increase particle motion, okay, or position. Okay, you can also think of that as position. So I think of it as distributing it from being a solid, where we would have, so I'll say position. I'm going to say position in this one. You can think of it either way, but think of if we have a solid that goes in here, say it's a chunk of sodium chloride, and then as the solution is forming, we know that those particles are going to be distributing throughout that solution. And so we're increasing the position of those as well as the motion, okay, and motion. And so this one's definitely going to be a spontaneous process. We see that solutions do form. And so that's kind of a good context to think about. All right, so those are just some kind of scenarios to think through. The last thing we're going to take a look at here is going to be standard entropy change of a reaction and the equation that goes with this. Okay, and so when we're doing all of these types of things, we can evaluate using some standard, okay, conditions. So our delta S, and we use that little prime under standard conditions, okay, so standard conditions, 298 and 1 atmosphere. That's where this little prime number is coming from. And so there's actually an appendix that has some values that you can look those up in the book, and I usually have a handout or I link something in OneNote for you. Okay, and so the sum of those values for the products minus the sum of those values for the reactants. Okay. And then just so we remember in this process, okay, so just a little thing to remember, because I don't write it out in the long format. I don't remember how the book writes it. So remember to multiply the values from that chart by the reaction coefficients. Okay, so the sum of all those products minus the sum of all of those in the reactants, and that's how you would determine that through a calculation.